So let's discuss a problem from GATE 2021 physics. So this is from quantum mechanics and it is related to the perturbation and first order energy correction. So here is the problem. Consider a particle in a one-dimensional infinite potential well with its walls at x equals 0 and x equals 1. So here we need to consider a particle in, so this is the infinite potential well. So the particle is inside this well and the boundaries are also given, that is from x equals 0 to x equals to L. So this is the well. So the system is perturbed as shown in the figure. So here they have given the system is perturbed. So here perturbation is also applied. So this is not a pure one-dimensional potential well. So if it were a pure one-dimensional potential well, it would have been like this, only this, x equals 0, x is equals to L, and this would have been infinity. Potential at that would be infinity, and the particle is restricted to move from here to here, only that. You cannot move anywhere else. So and here, but here it is given that here we can see this voltage, we can see this potential. So here not only here the potential is not only residing, so actually there would be infinite potential at both the edges, and in the middle the potential would be 0 in general for a infinite potential well. But here we can see the potential is changing, varying here from here to here, and finally it is coming to V of L is equals to V naught at this point. It is varying in this manner from here to here. So this is nothing but perturbation, and now we need to find first order correction to the energy eigenvalue. So because of applying this perturbation, so what is the energy eigenvalue? So it is varying, we can see. So eigenfunction for a one-dimensional infinite potential well with walls at x equals 0 and x equals to L. So in general, the eigenfunction for this one-dimensional infinite potential well is this n of x, that is for nth energy level, nth state, which is equals to root 2 by L, which is nothing but the length of the potential 0 to L. Here it is, so that is that L, and sine n pi x by L. So this is the potential in this case, but this is the potential we need to use. But if the edges were minus L by 2 to plus L by 2, that means here minus L by 2, here plus L by 2, then it would have been this cos n pi x by L, because sine formula we know that 0 L. So sine pi by 2 is 1. So in the place of x, if we substitute L by 2, what we would get? L would get cancelled, n pi by 2. For first energy state, what we would get? Sine pi by 2, 1. So because it maximum, this is the eigenfunction, eigen energy. So this is the eigenfunction shape, that is probability. So this is the probability curve you can see here. So probability or eigenfunction, whatever we can say. So the maximum probability of finding the particle would be here in general, if we think. So this suits well based on these values. But here if we see in this case, in this scenario, here also the probability of finding the particle would be maximum in the middle only, for the first energy level, for the ground state. So but here in the middle, what value we would get is 0, and we know that cos 0 is maximum, cos 0 is 1. So here if we substitute in the place of x 0, we would get cos 0, and finally root 2 by L, which is maximum. Hence we need to be very careful what are the edges, what is the boundary condition they have given. So in the problem, if we see here, they have given 0 and L, but not minus L by 2 and plus L by 2. So we need to use sine formula only. So this is the best in this scenario. So while doing this kind of problems, we should keep an eye on the boundary conditions. So we need to use this formula now. And next, this is from the diagram. So in actually what the diagram was, so this was the diagram, and the potential was varying in this manner. So it was varying like this, and here x is equals to 0 and here x is equals to L. Now we need to find a potential at somewhere. So in general we want a formula for potential V, because in this formula we need to apply. So now first we need to find out the formula for potential. So at some particular x, so at some particular value of x, let the potential be V. Now from this if we see, so this is a triangle and this is also a triangle, right angle triangles. So here let us suppose the angle is theta. So from the diagram, tan theta, so what is tan theta is opposite side. So this is opposite side and this is adjacent side. So now if we consider the case of this triangle, that is this, for this triangle, for this triangle, what is the opposite side? Opposite side is V. So this height is V, and adjacent side is x. From here to here distance is x. So so this is for the for this triangle. Now if we consider in the similar manner for the another similar triangle, so for this triangle also tan theta is nothing but, so for this triangle actually, so for this triangle what is tan theta? So opposite side by adjacent side. So at the opposite side they have given in the question, this is V0 at this edge. So V0, opposite side is V0 and adjacent side is L. From here to here the distance is L. From here to here the distance is V0. So V0 by L. So like this. Now if we take this both, and now if we calculate, so sending this x to that side, we would get this. So this is the formula for potential at any point. At any point. So only they have given potential at this end and at this end. They haven't mentioned anything about potential in the middle points. So we have derived the potential at some point x. Now we need to apply the formula for the first order energy correction, that is this En of 1. This is the formula for first order energy correction. So that is nothing but N of x, bra of N of x, we get N of x. So now as this is bra and this is ket, so this is nothing but conjugate of this wave function. So conjugate here they have given, we have, so this is the wave function we are using. So here conjugate, there is no term like I here. So the conjugate of this wave function is equals to that wave function only. Here the conjugate of the wave function is equals to that same wave function we would get. So root 2 by L sin pi x by L, which is same as the original wave function, root 2 by L sin n pi x by L, and this is the potential as we have seen in the formula. And now here root 2 by L is there, here also root 2 by L. Both of them multiplied together we will get 2 by L. And here in the place of V, we are having V0 by L into x. So V0 by L is a constant which is taken out, and this is x deciding inside the integration 0 to L. And sin n pi x into sin n pi x is nothing but sin square n pi x by L. sorry, sine by n pi x by L. So finally we would get this. And now we need to solve this integration. So here it is square. So we need to convert it into unsquared form. So we know the formula 1 minus cos 2 theta by 2. 1 minus cos 2 theta by 2 is nothing but sine square theta, or 1 minus cos 2 theta is nothing but 2 sine square theta. So if we take this 2 inside, 2 sine square theta could be written as 1 minus cos 2 theta. That is, here theta is nothing but equal to n pi x by L. N by x by L. So this is the value of theta. So 1 minus cos 2 theta, cos 2 n pi x by L. Now we need to split this, distribute it, and finally we need to perform integration. So here you can see it. So outside what would remain is this 2 has been taken out inside, so v naught by L square would remain, and we are integrating from 0 to L. And next here 1 minus cos 2 theta dx 0 to L. Now multiplying this with this, so integration of 0 to L dx x dx, and again with this. So here we would get integration of uv dx, and we need to use Eilert condition. Eilert, so inverse, logarithmic, algebraic, trigonometric, and exponential. So here algebraic comes first in the place of u, and then trigonometric, that is this trigonometric term. So we need to apply this formula. Integration of uv dx is nothing but u into integration of v dx minus integration of d by dx of u, which could be written as u dash whole into v dx whole dx. So here if we apply that formula, so after because of applying in the place of u x, in the place of v cos 2 pi n x by L, so we have applied that formula here. So and here integration of v dx, that is nothing but integration of cos x cos ax dx. Integration of cos ax dx is nothing but sine ax by a, that is sine ax by a. In the place of a we are having 2 pi n by a. So here this is nothing but a, 2 pi n by L. So that a we have got here. And next, and so here if we do integration, x power n plus 1 by n plus 1, 1 plus 1 by 1 plus 1, that is x square by 2, limits from 0 to L. And next here if we see, here after integration we would get sine n pi sine ax by a. And here also another, if we do again integration of sine ax is nothing but minus cos ax by a. So minus into minus would become plus here. We need to keep an eye on plus or minus signs also while calculating, so it's also very important. So and finally here we would get cos ax by a. So already here one a is there, and another a would come again because of another integration, so a square. So this is 1 by a square. A square is nothing but 2 pi nx 2 pi n by L, that is a. So 1 by a square is this. But however now if we apply the limits, so let us see what happens. So this is very important here. So here if you apply limit, upper limit minus lower limit, L square minus 0 square by 2, so L square minus 0 square by 2. And here if we see, this is very important. So if we apply upper limit, what would happen is here we would get L sine 2 pi n L by L. L would get cancelled, and what would remain is sine 2 pi n. Sine 4 pi, sine 2 pi, sine 6 pi, sine 8 pi, all of them are 0. So sine, it would become 0 this term. So 0 into x is 0. So that is it would become 0 if we apply upper limit. And if we apply lower limit, what it happens in the place of x, 0. So 0 into anything is 0, and here also sine 0 you would get. So this entire term becomes 0. And now we need to see what happens to the next term. Here also if we apply upper limit. So 2 pi n l by l, l will get cancelled, we will get 2 pi n. Sin 4 pi, cos 2 pi, cos 4 pi, cos 6 pi are all 1, cos 0 is 1. And if we apply lower limit minus cos 0, that would also be 1. That means we would get 1 minus 1, and this term also would become 0. So only this term would remain. So finally here this is nothing but L square by 2, L square cancel, V naught by 2. So this is the finally our value, required value. So this is the answer. This is the first order energy correction for the given perturbation, that is V naught by 2. So this is the correct option for this question. So this is the problem. So thank you.